Hi everyone, let's play a little game here with frequency histograms. Let's say a standardized test is given at a high school. Teacher A over here and teacher B over here both teach statistics classes, and they both administer the standardized test to their two classes. Let's say that these two teachers then report their frequency histograms to the principal. The first teacher, teacher A, gives the principal this frequency histogram on the left. Teacher B gives the principal this frequency histogram on the right. Now, at first glance, the principal might be thinking, oh, wow, look at this comparison here. Look at this comparison here. I see that the A students are over here on the right. They scored in the 90s percent-wise. Then the B students, then the C students, then the D students, then the F students over here. But it looks like teacher B over here is getting a much more impressive distribution. I see a lot of A's and B's over on the right and fewer D's and F's over on the left. Whereas for teacher A, it seems rather flat. It seems that there were roughly equal amounts of students getting A's, B's, C's, D's, and F's. So it looks like teacher B should get our prize, our Amazon gift card or whatever. Maybe you've seen Bad Teacher with Cameron Diaz. What do you think of this principal? Did the principal take a good statistics class? I'll give you a hint. The horizontal axes are the same. The classes are the same. Basically, F's, D's, C's, B's, and A's. We have the same horizontal axes on the two histograms. But look at the vertical axes, the frequency axes. Very different, aren't they? Teacher A, in a way, was kind of honest, started with 0 over here as the baseline. That seems natural. And the teacher is reporting 20 A's, 20 B's, 18 C's, 17 D's, and 17 F's. Guess what? Teacher B had the exact same results. 20 A's, 20 B's, 18 C's, 17 D's, 17 F's. Let's assume that all the students scored between 50 and 99 points on this exam. Hopefully it was out of 100 points, not 1,000. Otherwise, our schools are in bad shape. All right. The same data set, at least in terms of the numbers involved, yielded two very different looking pictures. Now, I cannot say that teacher A or teacher B necessarily gave a wrong or incorrect histogram, unless there was fraud or misreporting. That's possible. But it's possible that both teachers were honest, and these were honest reportings of their respective data. But the pictures can look different depending on how you rescale the axes or position the axes. These histograms may not be wrong, but there could be a misleading. And this could lead to statistical abuse and trickery. Okay, now let's go back to the President's Ages histogram. This was not intended to be misleading, right? Maybe Cameron Diaz, as Bad Teacher, was doing this second histogram over here. She maybe knew statistics. So learn statistics to be evil, trick people. All right, so what are some guidelines for histograms? All right. Scaling. The highest tick mark on the frequency axis, here's the 15 up here, must be at least as high as the highest frequency, which was 13, the height of the low 50s bar, among the classes. All right. So the modal class had a frequency of 13. Notice that that does not exceed the 15 over here. Okay. Otherwise, the bar would be extending past that top tick number. We need consistent spacing along each axis. All right. So notice the ages here. You know, the classes had the same widths. So each of these bars have the same widths. All right. Here we're going by 5s. 0 to 5, 5 to 10, 10 to 15. Now you don't have to go by 5s. You can go by 4s or 6s or even 10s. But don't go 5 here, 2 here, 15 there. That's no fair. You need equal spacing, even spacing along the axes. Consistent spacing. The tick marks and the numerical values on the frequency axis have to be evenly or equally spaced, and bars must have the same width. All right. The issues of different starting points and stretching or squeezing the frequency axis. So that explained why these two pictures look very different. On the left, teacher A started at 0. On the right, teacher B started at 16. Not that that was necessarily incorrect, but why 16? For that matter, why 0? Okay. Sometimes it's impractical to start at 0, actually. All right. Beware of statistical abuse. People might try to trick you based on whether they're trying to emphasize differences or de-emphasize differences. Watch out for charts or line graphs with the Dow Jones or the stock market, for example. You can see these kinds of tricks. The horizontal axis tends to be less controversial, but the vertical axis, people more often abuse. All right. Now, we talked about frequency histograms. We can also talk about relative frequency histograms. Basically, you're taking the frequency axis and you're rescaling it. Basically, you can get a relative frequency histogram by taking these numbers and dividing by capital N, the population size, 45. So here's a frequency histogram. The relative frequency histogram has the exact same shape. It's just that we divide these numbers here by 45. Now, these fractions look kind of weird. They're not even reduced. So it might be better to use nice decimals or nice percents. Okay. And then the heights of the bars here would correspond to the relative frequencies in decimal or percent form. And then you can do estimates. So for example, what proportion of the presidents were in their early 50s, 50 to 54 years old, when they became president? Well, a bit less than 30%, looks like. Proportion is a little bit less than 0.3. A little bit less than 0.3, a little bit less than 30%. Okay. You can get that from the relative frequency histogram. From the relative frequency table, you can see that the actual relative frequency was about 28.9%. Now, here, for both the frequency and relative frequency histograms, we saw maybe a very rough bell shape. What if we had this situation? A standard 6-sided die is rolled 100 times. And you record the frequencies for the 1s, 2s, 3s, 4s, 5s, and 6s. The number of times the die comes up, a 1, a 2, and so forth. Would you expect a bell shape? Would you expect a bell to come up 3 and 4 much more often than 1 or 6? Probably not. You'd probably expect more of a uniform distribution. Maybe not perfectly flat, but you'd expect more of a uniform distribution. The point being that not everything is bell-shaped. All right, next time, more pictures.